Welcome to the first lecture of this series. Before I begin, let me give you a useful information. If you want to know more about these lectures, the topics that I shall be covering, updates, etc., please visit the following website, which has been created by the Astronomical Society of India. This course, which is meant to be a survey of astronomy and astrophysics, is meant to be an introduction to the subject. Therefore, it's not going to be a systematic development of the subject. Nor will I dwell very much on the phenomenology, which is rather important in astronomy because we deduce everything from observations. Nor will I say much about the observational techniques, but you should read about them, and I shall give references as we go along. The main thrust of my lectures is going to be elucidating the underlying physics. My objective in doing this is the following. I hope the various topics that we shall discuss in the series of lectures will serve as illustrations of what you learn in your basic physics courses in the college, courses on thermodynamics, statistical physics, quantum physics, radiative processes, classical mechanics, nuclear physics, and so on. I shall divide the set of topics that we shall discuss into several units. The first unit will have 4 lectures. Today's lecture is on the theme, What are the stars? The second lecture will be on the principles of absorption and emission of radiation. The third lecture will be on the interesting question, why are the stars as they are? And the fourth lecture will deal with the energy generation in stars. So let us begin. What are the stars? In a sense, we shall begin where the subject of astrophysics began, in the beginning of the 19th century. This is our Sun, and what do we know about it? Well, its mass is 2 times 10 to the power 33 grams. I hope you know that. And how do we know that? Well, I'm not going to tell you how we deduce the mass of the Sun, but this is something that you should think about and deduce. The radius of the Sun is 0.7 million kilometers. Remember it as roughly a million kilometers. Its mean density is 1.4 grams per cubic centimeter, just a little greater than the density of water, which is 1 gram per cubic centimeter. And its surface temperature, which is what we can measure from here, is approximately 6,000 Kelvin. The subject of astrophysics was born when young Fraunhofer in Germany, in the year 1817, discovered dark lines in the spectrum of the Sun. He marked more than 600 such dark lines. He singled out the more prominent ones and labeled them and measured their wavelengths. This is a modern spectrum of the Sun in an incredibly narrow range of wavelength between 4,300 and 4,400 angstroms. And what you see are thousands and thousands of dark lines traversing the spectrum, just as Fraunhofer did. What you see here are emission lines. Emission lines from the Balmer series of the hydrogen atom. And what you see below are emission lines of iron. Obviously, this spectrum is much richer than the spectrum of emission lines from the hydrogen atom. Around the year 1860, the great German physicist Kirchhoff formulated 3 laws of radiation which are absolutely fundamental and we should really understand them. His first law states A luminous opaque body emits radiation at all wavelengths, thus producing a continuous spectrum as shown over there. The second law states a rarefied luminous gas emits radiation whose spectrum consists of a series of bright lines. Sometimes these bright lines are superimposed on a faint continuous spectrum, such as shown in this figure. The third law states if white light from an opaque luminous source is passed through a tenuous gas, the gas may absorb radiation at certain wavelengths so that the radiation at these discrete wavelengths will be either missing or diminished, thus producing dark lines as may be seen in the bottom picture. There is an ancient Chinese saying that one picture is worth 10,000 words. So let us restate the laws of Kirchhoff. The first law states that a luminous opaque body emits radiation at all wavelengths, thus producing a continuous spectrum, which is of course the black body spectrum. The second law states that if the radiation from an opaque states that a rarefied luminous gas emits radiation whose spectrum consists of a series of bright lines, sometimes superimposed on a faint continuous background. And the third law states that if the radiation from an opaque body passes through a tenuous gas at a certain temperature, then the result will be a continuous spectrum with the intensity either decrease or vanishing at some discrete wavelength. These are the dark lines of Fraunhofer. Now, Kirchhoff and Bunsen did a series of experiments detecting emission lines from heated metals. Here are some examples. This is sodium. What you see in the top panel are absorption lines at various wavelengths, and what you see in the bottom are emission lines at various wavelengths, and you notice that there is a precise one-to-one correspondence between the wavelength of the absorption lines and the wavelength of the emission lines. Down below is nitrogen. These are the dark absorption lines, and these are the emission lines. And this is hydrogen, absorption lines of hydrogen, emission lines of hydrogen, and down below is oxygen. From this, Kirchhoff and Bunsen deduce the following. They deduce that the dark lines in the solar spectrum that Fraunhofer had discovered are caused by absorption by chemical elements in the solar atmosphere. And thus, it became clear that stars are gaseous globes. So, by 1860, Kirchhoff and Bunsen had established that at least the outer layers of the sun and the stars are gaseous. The Fraunhofer absorption lines enabled one to identify the elements in the atmosphere of the sun and the stars. As we shall see, the interior temperature of the sun is roughly 10 million degrees, and therefore you would expect the interior also to be gaseous, not solid, not liquid, but gaseous. What are the stars? The positivist philosopher Auguste Comte, who was highly influential in European thinking, had asserted that it is in the nature of things that we shall never know the chemical composition of the stars. Not that our knowledge is incomplete, but we shall never know the chemical composition of the stars. The philosophers, including Auguste Comte, were wrong. Stars are globes of gas containing atoms of the same elements that we find on Earth. A great scientific revolution had begun. This is the sun. And the first thing you notice about the sun is that although it is gaseous, it appears to have a sharp surface. This is rather surprising. You expect planets which are solid to have sharp surface and not a blob of gas. This apparent surface of the sun is known as the photosphere. We have to understand this. The second thing that we notice about this image of the sun is that the limb of the sun is darker than the central region of the disk. This is known as limb darkening. We have to understand this also. But first, let us try to understand why the sun appears to have a crisp surface. As we shall soon see, the interior temperature of the sun is roughly 10 million degrees. At a temperature of 10 million degrees, atoms, all atoms, will be partially or fully ionized. Therefore, the stellar material is a plasma which consists of positively charged ions and negatively charged electrons moving around freely as a gas. If a gas is at a temperature of 10 million degrees, then according to Planck's law of black body radiation, then the radiation will be primarily at X-ray wavelengths. And these X-rays will be scattered by the free electrons in the stellar material. This scattering is known as Thomson scattering, and this was first discussed by the great physicist J.J. Thomson, who discovered the electron at the Cavendish Laboratory at the University of Cambridge. And what this picture shows is an incident photon scattering of an electron and going off in a different direction. Why does the electron scatter it? The incident radiation is a transverse electromagnetic wave with an electric field and a magnetic field perpendicular to one another in a plane which is perpendicular to the direction of propagation. An electron, since it has an electric charge, in response to the oscillating electric field will oscillate. And as we shall discuss in later lectures, an oscillating electron will radiate at the same frequency as the frequency of oscillation, and therefore what you would expect is that the frequency of radiation in the scattering process is not changed. It's an elastic scattering. The scattering cross-section, we shall introduce the notion of scattering cross-section precisely in the next slide, but I want to say right at the outset that the scattering cross-section in the Thomson scattering process is independent of the frequency. This is not true of all scattering mechanisms. What is scattering cross-section? An electron is not a point particle, it has a physical size. But for an electromagnetic wave, which is a combined transverse and electric and magnetic field which are oscillating, it subtends a certain area, and that area is known as the scattering cross-section. And the dimension of scattering, it is denoted by sigma traditionally, sigma subscript t for Thomson scattering. Now, this scattering cross-section has a dimension of centimeter squared, which is area. The scattering cross-section in the Thomson scattering process is given by this very simple formula, 8 pi by 3, the square of E squared by mc squared. What is E squared by mc squared? It is the dimension of length, and that length is known as the classical electron radius. What is the significance of this classical electron radius? If a charge E is distributed uniformly in a sphere of radius r, then the electrostatic energy is of the order of E squared over r. And when this electrostatic energy is equal to the rest mass energy of the electron, which is mc squared, that equation, E squared by r is equal to mc squared, defines the classical electron radius. So what Thomson said was the scattering cross-section of an electron is the square of the electron classical electron radius, and its numerical value is 6.7 into 10 to the power minus 25 square centimeters. Please put in this constant and verify this value. Now let us discuss the mean free path of the photons, the X-ray photons inside the sun and the stars. As the photon is scattered, it will travel different lengths between the scattering. The average or the mean value of the distance it travels between two consecutive scattering is known as the scattering mean free path. And the mean free path is usually denoted by the symbol L. It is equal to 1 divided by n sigma. And what is n? N subscript E is the number of electrons per unit volume. And sigma t is the scattering cross section. You notice that the number density of electron has to come in the denominator. More the number of electrons per unit volume, more will be the scattering, and therefore smaller will be the mean distance traveled between the scattering, and therefore it has to come in the denominator. Similarly, the mean free path must be inversely proportional to the scattering cross section. If the scattering cross section is larger, then the mean free path will be smaller. Please notice that this is the dimension of per centimeter cube, this is the dimension of centimeter squared, therefore the mean free path has the dimension of a length, and it is approximately 2 centimeters. Now the density of the sun is not uniform, it varies, so if you do a more proper calculation, you find that the mean free path, or the average mean free path, averaged over density that is of the order of half a centimeter. Therefore, a photon which starts at the center of the sun, as it tries to escape from the surface of the sun, is doing a random walk like a drunken man. And that random walk of the photon is shown in this diagram. Let us say that the length of each step is the same for simplicity, and let's call the length of the step as small l. And let us say the photon is scattered n times. And the question we want to ask is, what is the distance it would have traveled, what is the distance capital D it would have traveled after n steps of length L? Well, of course, if the path was rectilinear, then the distance it will travel after n step of length L will simply be equal to n times L. But because the walk is random, it will be less than n times L. And Einstein was the first person, as far as I know, in his famous paper on Brownian motion in 1905, to deduce this formula that the distance traveled after n step of random walk, each step of length L is not equal to n times L, but it is equal to square root of n times L. So it's much less than n times L. Now, the problem we want to solve is the following. A photon starts at the center and it reaches the surface of the sun. How long does it take? And the time I have indicated as tau escape. Well, between each scattering, the photon travels a distance of half a centimeter at the speed of light, because there is no scattering. Therefore, the time for escape is simply the time taken to take one step multiplied by the total number of steps. The time taken to take one step is simply equal to the length of the step L divided by the speed of light L by c. Therefore, let us use the result we have obtained in the previous slide, namely the square of the mean end-to-end distance capital D is equal to n times L squared. let us simplify this equation and write the number of steps needed to travel a distance capital D is d squared by L squared, and of course in this case d is the radius of the sun, because we are talking about the photon escaping from the surface of the sun. Therefore the number of steps, each approximately half a centimeter, the photon has to take before it reaches the surface is equal to the radius of the sun whole square divided by the square of the mean step length. And if you put in the value for the radius of the sun, the speed of light, and half a centimeter for the mean free path, then you get approximately 50,000 years. So a photon takes 50,000 years to travel a distance of 1 million kilometers, reaches the surface, and then it travels the remaining 150 kilometers before it reaches the earth in a mere 8 minutes. Now, this photosphere which I had introduced, which is the apparent sharp surface of the sun, is the surface from which the photon eventually escapes to infinity and travels at the speed of light. So the photosphere is the surface of last scattering. In the case of the sun, our estimate suggests that it will take a photon approximately 50,000 years to diffuse from the center and reach the surface, and then travel to the earth in a mere 8 minutes. Now in the case of a star which is 10 times the mass of the sun, and therefore approximately 10 times larger in radius, it will take a lot more time. It may take 1 million years, or in more massive stars, many millions of years. Now let's try to understand the limb darkening of the sun based on the principles that I have just explained. When we look straight at the center of the disk, you are looking at, say, the point A. And I'm going to argue that when you are looking from the right here towards the point A, the center of the disk, then the radiation of the surface of last scattering is really the point, this solid sphere on which the point A is located. What does it mean? Once the photon from the center reaches the point A, the probability of subsequent scattering is negligible, and therefore it can escape. Let us say the probability of escape is 50%. Well, you like 40%, take whatever you like. Therefore, that is the surface of last scattering when you look at the disk of the sun. But when you look at the limb of the sun, the surface of last scattering is a larger sphere, the dashed sphere, and the point B is located over there. Why is the surface of last scattering a larger surface of a larger sphere? That is because you want the probability of escape to be the same from point B as point A. Therefore, the length of this cylinder has to be the same as the length of that cylinder. And because you are looking at an oblique angle, when you look at the limb of the sun, the point B will obviously be at a larger radius. Now the important thing is the following. We know that there is a net flow of radiation from the center to the surface of the sun. Therefore, the interior is hotter than the outer regions of the sun. And therefore, the sphere on which point A is located is a hotter sphere than the sphere on which the point B is located. It is slightly cooler. Now we know from Planck's law that at any frequency an opaque body radiates more if it is at a higher temperature, according to the law that the luminosity is equal to sigma T to the power 4. So that explains the limb darkening of the sun. When there is a total eclipse, one sees the remarkable phenomena of the corona. And when there is a total eclipse, astronomers gather all over the world at vantage points to study the total eclipse. One such eclipse occurred in the year 1868. It's a very famous eclipse, and astronomers gathered in various vantage points on the surface of the earth. One such place was Guntur, presently in Andhra Pradesh. Astronomers from France, England, Scotland, Ireland, you name it, they were all there. Just before the moon completely covers the sun and there is total eclipse and the corona shines, one sees a thin region of radiation which is known as the chromosphere. The light from this is brightly colored and hence the name chromosphere. There it is. What the astronomers in Guntur did was to send the light from this chromosphere through a prism or a grating and look at its spectrum. And you see the various emission lines are clearly seen. You will say, no, that's not possible. Emission lines have to be straight. Absorption lines have to be straight. Question is, why are emission lines, absorption lines straight? In a spectrograph, there is a slit right in the beginning. And what the spectrograph images is really the slit. And because the slit is straight, you have straight absorption lines and emission lines. In the case of the chromosphere, you do not need any slit because the radiation is coming from a very narrow region. So you simply pass it through a dispersing element like a prism or a grating. And this spectrum is known as the flash spectrum because you can only see it for a few seconds. Because a few seconds later, the moon completely covers the sun and you have the corona. In this spectrum, in Guntur in 1868, helium was discovered for the very first time. And the person who detected this remarkable new element was the French astronomer Jules Janssen. And what he noticed was this new line, bright yellow line, very intense, was adjacent to the very famous D1, D2 lines of sodium. But what is interesting is whether all these emission lines could be identified with specific elements through terrestrial experiments such as the one Kirchhoff and Bunsen had carried out in 1860. There was no terrestrial analog of this bright yellow line. And the British astronomer Sir Norman Lockyer called it helium because the Greek word for the sun is helios. So a new element about which we knew nothing had been discovered in the sun. Well, it turned out that 18 years later, helium was discovered on Earth trapped in rocks. It was isolated, its atomic mass was determined, and all the properties were elucidated. And then, of course, the other rare gases were discovered. Let us now turn to the question, how hot is the sun? How hot is the interior of the sun? Now you may say, how can we ever know? We have never been there. All we can see is the surface of an opaque body. Well, we can. And what we shall do is to use a very well-known theorem in physics known as the virial theorem. This is valid under very general conditions, and you can read about that in books. For example, Classical Mechanics by Goldstein or Landau and Lifshitz, or any standard book on physics will discuss the virial theorem. What the virial theorem says is that the total energy of the system is equal to 1/2 the potential energy of the system. Is this really true? Well, let's try to apply it to a problem that we've all solved in our school days. The satellite problem, in which a mass small m is going around a mass capital M. Well, we know Newton's laws, and the total energy of the planet is its kinetic energy half mv squared plus the gravitational potential energy of the planet arising due to attraction by the central mass capital M. The gravitational potential energy is Gmm by R, and of course the gravitational potential energy is negative. Now we can simplify this equation. We can get rid of the velocity by using the force equation, which is the left hand side is the centrifugal force experienced by the planet, which is mv squared by r, and the right hand side is the gravitational attractive force experienced by the planet. We can use this equation to rewrite the first equation as follows. The total energy of the planet is equal to 1/2 the gravitational potential energy. The gravitational potential energy is given by minus G capital M small m divided by R. Let us now apply this to the sun. The statement is still the same. The total energy of the sun is equal to 1/2 the gravitational potential energy. What is the total energy? The total energy is the total thermal energy of the gas plus the gravitational self-energy of the sun. Therefore, the total energy is the thermal energy plus the gravitational potential energy, that is equal to 1/2 the gravitational potential energy. Therefore, the thermal energy is equal to minus 1/2 gravitational potential energy. You will say, well, that cannot be right. Thermal energy cannot be negative. Well, it is indeed positive, because please remember that the gravitational potential energy itself is negative. Therefore, the right hand side is positive. Now, recall that this statement really follows from the first law of thermodynamics. If you are interested, convince yourself of that. Now let us apply this to the sun. Therefore, Virial theorem says that the thermal energy of the sun is equal to 1/2 the gravitational potential energy, which is 1/2 Gm squared divided by R. Please remember that if I have a sphere of mass m and radius r, its potential energy, self-energy, is Gm squared divided by capital R. What is the thermal energy? It is the kinetic energy due to thermal motion of an individual particle, which is 3/2 kT. You remember each degree of freedom is half kT, therefore in 3 dimension it is 3/2 kT, and the total number of particles in the sun is capital N. Now we can substitute for the total number of particles Boltzmann's constant, Newton's constant of gravity, mass of the sun and the radius of the sun, and solve this equation for the temperature of the sun. We know all these things. How do we know the number of particles in the sun? Well, let us assume for simplicity the sun is made primarily of hydrogen. We know the mass of the sun. So if you divide the mass of the sun by the mass of the hydrogen atom, then you will get the number of hydrogen atoms in the sun. Therefore, since it's ionized, you will get the number of protons and number of electrons in the sun, and that number is approximately 10 to the power 57. Please put in the numbers and convince yourself that the total number of particles in a star like the sun is indeed of the order of 10 to the power 57. If you put in all these things, you get this marvelous result that the average temperature of the interior of the sun is 10 million degrees Kelvin. Isn't it marvelous? So, there is the sun, but its surface is only at 6,000 Kelvin. Why is that so? Well, there is really a blanket surrounding the sun, and the temperature of that blanket is 6,000 degrees. Why is it so low? Well, that has to do with some very interesting physics, such as the existence of negative ion of hydrogen, a hydrogen atom with a second electron, and things like that. I don't want to digress at the moment and go into the very interesting physics. Perhaps you can read about it. But for our purpose, we shall ignore the surface temperature of the sun, and we'll regard the sun as a gaseous blob with an average temperature of 10 million degrees. So the question now is the following. When we look at the center of the sun, or anywhere in the disk of the sun, what we see are absorption lines superimposed on the continuous spectrum of an opaque body. But when we look at the limb of the sun, as during just before total eclipse, for example, you see emission line superimposed on a weak continuum. Why is this so? This is a fundamental question, and we simply have to understand this thoroughly and deeply. That we shall discuss in the next lecture, in which we shall discuss the principles of radiative transfer and the principles of absorption and emission of radiation. But let us now move on to the question, what are the stars? As I said, in the 1870s, following the pioneering work of Kirchhoff and Bunsen, various people, Lane, Lord Kelvin in Scotland, Helmholtz in Germany, Emden, and various other people had formulated a theory of the stars, the sun and the stars, as globes of perfect gas. What they said was the following. A star is stable because the inward pull of gravity is precisely balanced by the pressure of the gas. This pressure is to be calculated according to Boyle's law. So what they are trying to say is that if there was only gravity, then the stars will be crushed out of existence because gravity is attractive and the star will collapse to a point and disappear. Therefore, there has to be something that opposes the inward pull due to gravity. And what that force is the force due to gas pressure. Pressure is force per unit area. So when you press on the piston of a cycle pump, it is easy in the beginning, then it gets harder and harder, then finally you cannot push the piston any further. And if you touch the cycle pump, it will feel hot. Why does it feel hot? I have converted half of the work I have done into internal thermal energy. And that pressure of the gas is preventing me from pushing the piston down. And the same principle applies in the stars. What is the gravitational pressure at the center of the sun? Well, that's a very simple problem. There at the center of the sun, you construct a unit cylinder. What is a unit cylinder? Its surface area is unity and its length is the radius of the sun. And all you have to do is to calculate the weight of the material, stellar material in that unit cylinder on the top of your head. That is the gravitational pressure. And I'm sure all of you know how to do this calculation. If you have not done it before, please do it. But let's make a simple poor man's estimate. It's always good to do that before one plunges into detailed calculations. The gravitational pressure at the center is equal to gm squared by r to the power 4. Why? Let us imagine that the sphere is cut into two halves and separated by a distance roughly equal to the radius of the sphere. There will be gravitational force between the two hemispheres, which is m by 2. We'll forget the 1/2. We'll regard it as m. So the gravitational force is g m divided by r squared. And that gravitational force is acting on a surface area which is pi r squared. Therefore, the gravitational pressure, which is force per unit area, is of the order of gm squared divided by r to the power 4. Now, if you use calculus and do a proper calculation, you will find a numerical coefficient here, which is not very different from 1. You should know how to do that, and you must do it. But more importantly, you must appreciate that the gravitational pressure is proportional to the square of the mass and the fourth power of the radius of the star. Now we are all set to discuss the fundamental principle of mechanical equilibrium, which is known as the equation of hydrostatic equilibrium. What the hydrostatic equilibrium says is that let us consider an infinitesimal cylinder over here. There is gravitational force acting on it. And this gravitational force has to be balanced by the pressure differential across the two faces of the cylinder. So let's do this slowly and systematically. Let us consider this unit cylinder. Its cross-sectional area is unity and its length is dr, the distance between these two circles. Therefore, the volume of this infinitesimal cylinder is just dr, it is 1 into dr. Let us say that the density at this location is rho bracket r, or simply rho. Then the mass of this unit cylinder is rho times dr. And what is the gravitational force acting on it due to the rest of the star? As you know, in Newton's gravity, the mass exterior to the unit cylinder does not contribute, it cancels out, and it's only the mass interior to the unit cylinder that pulls it inwards. So, the gravitational force acting on this unit cylinder of mass rho dr is minus g m of r, which is the mass interior to r, rho dr divided by r squared. And the statement here is that this force should be balanced by the pressure gradient between the lower portion of this unit cylinder and the upper portion of the unit cylinder. Why should there be a pressure differential? That's explained in the next slide. This is our unit cylinder, if you like, rotated to make the figure simpler. And the cross-sectional area is unity and the length is dr. This slab is being bombarded from below and from above by particles which have kinetic energy. Therefore, there is a momentum transfer and therefore they exert a pressure. Now, as we go in towards the star, the temperature as well as the density increases, and therefore the number of particles per unit volume below the slab will be greater, and because the temperature is more, their average energy, which is 3/2 kT, will also be more than this. And that I have indicated by thicker arrows and thinner arrows. So the slab is being bombarded from above and below, and there is a net pressure differential because of the temperature and density gradient. Remember, in Boyle's law, the pressure is proportional to the density as well as the temperature. What is Boyle's law? Boyle's law states that the pressure of a gas, ideal gas, is nkt, where n is the number of particles per unit volume and k is Boltzmann's constant and T is the temperature. What particles? Any particle that you like. In the case of the sun, the electrons contribute, the protons contribute, the ions contribute, because they all have the same energy, 3/2 kT. They may have different velocities, but they have the same energy. Why am I bringing the energy into it? Because according to thermodynamics, the pressure of a non-relativistic gas, that means particles are moving with velocities small compared to the speed of light, is 2/3 internal energy divided by the volume. In other words, the pressure is 2/3 the energy density. Well, what is the internal energy? It is the number of particles multiplied by the average energy of the particle. The number of particles is capital N. The average energy is 3/2 kT. Therefore, if I divide U by the volume and multiply by 2/3, I get the pressure is equal to nkt, where n is the density of particle or number of particles per unit volume. Therefore, the equation of hydrostatic equilibrium states I have brought in the dr from the right hand side to the left hand side denominator. It says dP by dr, which is the pressure gradient, is equal to minus gm rho by r squared, where everywhere one has to calculate the mass interior to the point r. It's a function of r, the density at the point r, the pressure at the point r, and the pressure is nkt, and everything has to be calculated at the point r. The principle of hydrostatic equilibrium says that this fundamental equation has to be satisfied at all points in the star at all times. For a star to be mechanically stable, this equation has to be satisfied at every point in the star. If the condition of hydrostatic equilibrium is violated, for example, if the pressure changes very suddenly, the star will no longer be in hydrostatic equilibrium, it will be mechanically unstable, there will be motion, and the punishment will be rather swift. Let us say the pressure changes very suddenly. How long will it take to re-establish hydrostatic equilibrium? That is given by a time scale which is known in the literature as the dynamical time scale. Can we estimate this dynamical time scale? We can do that by taking the extreme case, by saying that let's switch off the pressure completely throughout the star. That the star will simply collapse due to Newton's gravity. Let us calculate what will be the time of this collapse. Well, this problem is the same as the following problem. Let us dig a tunnel on the surface right through the center of the earth to the other side, and let us drop a stone and calculate what is the free fall time of the stone from the surface to the center. Now, I am not going to do this for you because you have all studied Newton's laws and you should be able to calculate this free fall time scale. But you can make life easy by assuming that the density of the earth is uniform. It's not uniform, but a simple estimate can be derived by assuming that the density is uniform. Convince yourself that the free fall time scale of the stone to reach from the surface to the center of the earth is equal to 1 over square root of g times rho, where g is Newton's constant of gravity and rho is the density. This is the free fall time. And of course the stone is not going to stop at the center, it will go right through to the other side and it will oscillate and there will be simple harmonic motion. Convince yourself that the period of this simple harmonic motion is also given by this same formula 1 over square root of g rho. It's a very beautiful result. Please do this and convince yourself. Now, if you were to do a more proper calculation using calculus and so on, then you will find that the free fall time scale, which is an estimate of the dynamical time scale, is square root of 3 pi divided by 32 g rho. 3 pi is approximately 10, so 10 divided by 32 is 1 by 3 and there is a square root. Therefore, our simple estimate is off only by a factor of 1 over square root of 3. Is not too bad for an extremely simple-minded estimate. Now, if you substitute Newton's constant of gravity and the average density of the sun, which is 1.4 grams per cubic centimeter, you will find an estimate of the dynamical time scale as 30 minutes. In other words, if you mess around with the pressure in the star, the punishment will be swift and it will be handed out in a time scale which is as short as 30 minutes. So that concludes our discussion for the moment of what are the stars. In the next lecture, we shall attempt to understand this rather curious phenomena which we left unfinished, namely, why is it that when you look at the disk of the sun, you see absorption lines, whereas if you look at the limb of the sun, like just before a total solar eclipse, you see emission lines from the chromosphere. And that will take us to the subject of principles of radiative transfer and the principles of absorption and emission of radiation. Thank you.